in practice. We're going to break this down into 5 short videos. First one is going to cover definitions and basic terms. Second one covers simple DC motor. We'll build a math model of that DC motor using MATLAB and Simulink. Part 3 will do proportional, integral, and PI control of the motor velocity, kind of like controlling a robot's speed. Part 4 we'll talk about some practical things and some tuning rules. In Part 5 we'll talk about controlling motor position and why you want to use a PD control as opposed to the PI control that works so well for velocity. So let's start with some basics. What is PID? PID stands for proportional, integral, derivative. There are 3 components of a controller that we can implement independently or all together. It's a pretty useful general purpose control algorithm. It's been around a long time. People tend to use it for just about everything. Most of the time when we implement this, we'll just implement it as a PI control. The D part can be kind of, derivative can be kind of messy, and it's typically not used or typically not needed. If you need it, obviously add it. But one big exception is when we're doing position control, like the angle of a robot arm. You're much better off with a PD or even a PID than you are with the PI, and we'll get to that in the last video. Definitions. When we talk about proportional, what do you mean? It means here that the calculated value is some fraction or some multiple of the input. So our output y is a constant, proportional constant, k sub p in this case, of the input x. So here I have a graph where this line is x, and I have a line that's 1.5 times x, and I have a line that's 0.5 times x. So each of those blue lines and the red lines are proportional to the black line, okay, because they're just a constant fraction or constant multiple. I can also look at something proportional to a function. Our output y is equal to our constant k sub p times some function of x. And in this case here, I've got a sine wave drawn here in black, okay, and I have the red and green lines, change colors on you, huh? Red and green lines, which are proportional to the output of that sine wave. So here where the sine wave has a value of 1, this line is 1.5, this line is 0.5. You know, it's 1.5 and half times again. So that's what we mean when we say proportional. Derivative. Well, here we're getting into a little bit of calculus, and I'm not going to go into a rigorous, mathematically correct definition. I'm just going to try and touch on it to give you guys a feeling for what it means and how it works. It's the rate of change of a function output in response to the change in the input or inputs, denoted y dot, or the derivative of y is dy by dx, or essentially the change in y divided by the change in x, okay? Graphically, we can think of it as a slope. So here's my blue line here on the left is my sine wave. If I pick one point on this graph, I can look at a change in x, delta x, and see what the change in y, the dy, is, and that is effectively the slope of that graph at that point, or the derivative. On the graph on the right, I've taken that same sine function and I plotted in the red dotted line the derivative of y with respect to x at each point. So here at the beginning, we see that the slope is positive and it's actually equal to 1, so our derivative is equal to 1. As we get to the top of the curve, the slope goes to 0, so we get no change in y, so our derivative is 0 right there at pi over 2. And as we get to pi, as we approach pi, we see our slope is negative now. The line is going down, and our derivative is negative. Okay, and then it finally gets back down here to negative 1 at x equal to pi. Integral. The integral is an accumulation, or the area under the curve. It's the opposite of the derivative. We denote it here with the integral sign. We say that y equals the integral of some function of x times that delta x, or change in x. So graphically, we can say that it's the area under the curve. So if this is my function, at this value of x, we've accumulated or integrated this much underneath that curve as we've gone, okay? So here I plot it continuously on the graph on the right. This is my function. Starts out at 0. We start accumulating as this thing, and so our derivative goes up and up and up. Excuse me, our integral. Here our slope is 0, right? But we're still accumulating under this curve, so our integrator keeps climbing. Even though our value is going down, we're still accumulating area under there, so our integrator keeps on increasing. And here we hit 0. So at this point, we're not accumulating any more area underneath there. You know, we're just adding 0 each time, and our integrator term flattens out. And the way we'd implement this in software, typically we'd say that y equals y, where that's the previous version, plus some delta, some small amount that we've added from the previous implementation loop, or computational loop. Why would we go to all this screwing around, and why do we do calculus? Well, the fact of the matter is, Sir Isaac Newton invented calculus because he had to. He had developed his laws of motion, his laws of gravity. He needed to show that they would apply universally to everything from dropping an apple to the motion of the planets around the sun. So the way he was able to do that is he used calculus, invented and used calculus, to take his equations of motion and his laws of gravity and derive Kepler's planetary motion laws, and show that he came up with the way that we know the planets moved just based on his theory. So he invented it because he had to. You know, it's really the way, it's the kind of language that you need to describe mathematically how things happen in the real world. So it's not just, you know, to make life miserable for students. So some examples here. If I have, you know, if I say that a westbound train leaves Chicago at 3 p.m. and it travels 30 miles an hour for 1 hour, how far has it gone? That's pretty straightforward. 30 miles an hour times 1 hour, it went 30 miles. That's kind of an algebraic solution. But if I were to say the train starts at a speed of 0, accelerates to 30 miles an hour, drives 30 miles an hour some period of time, slows down to 15 miles an hour, does 15, speeds up to 40 miles an hour, and continues on to 40 miles an hour for a period of time. Now how far has it gone? That's not quite as simple to solve, right? Because we don't have just an algebraic relationship here. The way to solve that problem is to take the velocity as a function of time and times each delta time interval and integrate or accumulate that, and that gives us distance. So as I accumulate under this curve, that actually this area under here equates to the distance that I've traveled in that period of time. So for each delta time here, I'm going 30 miles an hour for some delta time. I multiply that 30 times that delta time, and I get the distance that I traveled in that little interval. So that's how that's how we get from velocity to distance. Now, if I don't measure velocity, suppose I'm measuring acceleration. How do I get from acceleration to velocity? Well, again, I integrate. So if my acceleration, for example, let me draw acceleration to match this. I accelerate for a while until I get up to 30, then I stop accelerating, and my acceleration is 0. Then my acceleration goes negative, stays negative for a short period of time, it goes back to 0, and then it goes positive until I get up to 40. That's supposed to be a straight line, and it goes back to 0 like that. So that's my plot of the acceleration as a function of time, and by integrating that, so here I'm accumulating positive values. My velocity is getting higher, right? Here it's 0, so I'm not accumulating anymore. My velocity is constant. Here I'm accumulating negative stuff, so my velocity is going down. Velocity is constant. Velocity is increasing, okay? So I can get from acceleration to velocity from velocity to distance, and I can go the other direction as well. If I've been writing down on a piece of paper the distance that I've traveled at certain time intervals, derivative of distance with respect to time, I get velocity. I can take the derivative of velocity, I get acceleration. So I can travel through this space here of distance, velocity, and acceleration, getting from one to the other, whatever I have to whatever I need, by either integrating or differentiating. And again, that's how the natural world works, and that's why this kind of stuff is actually important. One more definition here, control system. Control system consists of a number of parts. We have a controller. Could be proportional, could be PID, could be PD, could be some other control algorithm, but there is some kind of controller. Controller typically includes feedback, a measured value of the output. So if I measure my output and feed it back here, that goes into my equation. I have a physical plant, and I'll use the word plant throughout this lecture, just because that's a convention for control system things and habit. In our example that we're going to be using, I'll have a model of a DC motor. Okay, it's something that you give it an input, and our examples will give it a voltage, and it gives you an output. In this example, our output will be the speed or the angle. Okay, and that gets fed back. We have a target operating condition or set point. Here our target is 500 RPM, and what we do is we take the target, the speed we want to travel at, we subtract the measured output speed, okay, and we get an error. And the error is the input to our controller. The output from our controller is what goes into the physical plant, and the physical plant produces the system outputs that we want. If we're driving a robot across the room, we want the wheels to turn. We're generating motion and torque and velocity. So those are the outputs of our plant. So that's our basic definitions. Part 2, we'll put together that model of that DC motor. We'll start controlling it with a P controller and I controller, PI controller. Part 3, we'll talk about tuning and some practical things in Part 4. And Part 5, we'll talk about position. And I hope you're finding this helpful and not scared off by the calculus, because it's really not calculus-y calculus. It's pretty basic stuff. But you'll find it essential as we go to understand what that really is. So thanks for listening, and I'll catch you in the next part.